Welcome back to Computer Lessons.
If you could see the world as a computer sees it, your living room would not be empty space. It would be a chaotic storm of invisible energy. Pulsing spheres of light would be expanding from your router, bouncing off walls, passing through your body, and shattering into reflections. This is the realm of Wi-Fi, a technology that feels like magic but is actually just advanced physics. At its core, Wi-Fi is simply light that you cannot see. It occupies a specific slice of the electromagnetic spectrum known as radio waves. Just like visible light has different colors based on frequency, radio waves have different channels that allow multiple devices to talk at once without screaming over each other. The two most common colors of Wi-Fi are 2.4 GHz and 5 GHz. The term hertz simply means cycles per second. A 2.4 GHz wave oscillates 2.4 billion times every single second, creating a wavelength about 12 centimeters long. This physical length is crucial because it determines how the wave interacts with matter. Longer waves, like 2.4 GHz, are better at wrapping around obstacles and penetrating solid objects like concrete walls. This is why your old router still connects in the backyard, even if the speed is slow. In contrast, 5 GHz waves are shorter and more fragile. They carry more data because they oscillate faster, allowing us to pack more information into each second. However, they struggle to pass through walls. A single brick wall can absorb a significant portion of the signal's energy. But why did we choose 2.4 GHz in the first place? The answer lies in your kitchen. In 1947, engineers discovered that water molecules resonate and heat up at roughly this frequency, leading to the invention of the microwave oven. Because high-powered microwave ovens would inevitably leak some radiation, international regulators designated 2.4 GHz as an ISM band: industrial, scientific, and medical. It was a junk band where anyone could operate unlicensed devices. Wi-Fi was born here specifically because it was free to use, not because it was the best frequency. This historical decision created a massive problem: interference. Your Wi-Fi has to fight for airtime against microwaves, baby monitors, Bluetooth speakers, and your neighbor's router. This is why internet speeds often drop in the evening when everyone comes home and starts streaming. To manage this chaos, Wi-Fi divides the frequency into smaller lanes called channels. In the 2.4 GHz band, there are only 11 channels in North America, and they overlap significantly. Imagine a highway where cars in lane 2 are wide enough to block lane 1 and lane 3. This is why technicians always tell you to use channels 1, 6, or 11. These are the only 3 channels that do not overlap with each other. If you and your neighbor are both on channel 6, your routers are forced to take turns speaking, cutting your speed in half. But how do we actually send a 0 or a 1 over a radio wave? We use a technique called modulation. The simplest form is changing the amplitude or loudness of the wave to represent data. Modern Wi-Fi uses a wildly complex modulation scheme called QAM, or Quadrature Amplitude Modulation. Instead of just changing the volume, we change the phase, the timing of the wave, and the amplitude simultaneously. Imagine throwing a dart at a dartboard. The angle of the throw represents the phase, and the distance from the center that represents the amplitude. By targeting specific spots on the board, we can transmit multiple bits of data in a single wave cycle. Wi-Fi 6 pushes this to 1024 QAM, meaning the router is distinguishing between 1024 microscopic variations in the signal. This requires incredibly precise hardware. If there is too much background noise, like a running microwave, the router cannot distinguish these tiny variations. It automatically drops down to a simpler modulation scheme, which is more robust but much slower. Unlike a wired Ethernet cable where you can send and receive at the same time, Wi-Fi is half duplex. It is like a walkie-talkie conversation. Only one person can talk at a time. If two devices transmit simultaneously, the waves collide and destroy the data. To prevent this, Wi-Fi uses a polite protocol called CSMA/CA, Carrier Sense Multiple Access with Collision Avoidance. Before your phone sends a packet, it listens to the air. If it hears energy, it waits a random amount of milliseconds before checking again. This listen before talk mechanism is why Wi-Fi feels slow in crowded areas like airports. Your phone isn't transmitting slowly. It is spending 90% of its time waiting for a moment of silence to speak. Efficiency drops dramatically as more users join the network. To measure signal quality, we use a unit called decibels per milliwatt, or decibel milliwatts. This scale is logarithmic and negative. Minus 30 decibels per milliwatt is a perfect signal, while minus 90 decibels per milliwatt is basically unusable noise. Because the scale is logarithmic, a drop of just 3 decibels per milliwatt means you have lost half of your signal power. Moving your router from behind the TV to an open shelf can literally double the energy reaching your device. Physical placement is the single most important factor in network performance. Modern routers have introduced a physics hack called MIMO, multiple input, multiple output. Old routers had one antenna. Modern ones have 4, 6, or 8. They use these antennas to send different data streams on the same frequency at the same time. They achieve this by taking advantage of multipath propagation. Normally, radio waves bouncing off walls causes confusion, like an echo in a large hall. MIMO routers use the bounces intentionally, calculating the different arrival times to separate the signals. Even more advanced is beamforming. Instead of broadcasting the signal in a perfect circle like a light bulb, the router analyzes where your phone is located. It slightly delays the signal on specific antennas to create constructive interference patterns. This focuses the radio energy into a directed beam aimed straight at your device, extending range and speed. It acts like a sniper rifle of data rather than a shotgun. This is standard in Wi-Fi 5 AC and Wi-Fi 6 AX standards. Speaking of standards, the confusing names like 802.11n and 802.11ac are finally gone. The industry has rebranded to Wi-Fi 4, 5, 6, and now Wi-Fi 7 to make it easier for consumers. The latest leap, Wi-Fi 6E, opens up a brand new frequency band, 6 GHz. This is the biggest upgrade in history because the 6 GHz band is wide open. It has no microwave ovens, no baby monitors, and no legacy devices. It offers massive 160 MHz channels that allow for multi-gigabit wireless speeds previously only possible with cables. However, all this speed is useless without security. An open Wi-Fi network broadcasts your data in plain text for anyone with an antenna to read. This is why we use encryption protocols like WPA2 and the newer WPA3. These protocols scramble the data using complex mathematics. When you enter your password, you are establishing a handshake. This handshake generates a unique, temporary encryption key for your specific session that changes constantly. Wi-Fi has liberated us from the desk, but it has limits. Radio waves can only travel so far before the signal fades into the background radiation of the universe. To connect continents, we cannot use air, we need glass. The true backbone of the internet lies at the bottom of the ocean. In the next video, we will dive deep into fiber optics and submarine cables, the hair-thin strands of glass that carry 99% of global data traffic.
Tell me in the comments, do you live in a congested apartment building where the 2.4 GHz band is unusable, or are you lucky enough to have a clear spectrum? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.